Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today's topic of discussion is engineering notation and prefixes. Our objective today is to learn to employ engineering notation and prefixes. Additionally, we'll discuss engineering format as used on scientific calculators. The goal of engineering notation and engineering prefixes is to make unusually large and unusually small numbers easier to write, read, and most importantly, conceptualize. Consider the unwieldiness of numbers like 560,000 volts, 10 million ohms, 0.0000020 amps, and 0.00000000033 farads. At first glance, all the zeros blend together like a herd of zebras trying to confuse a predator. And there's no way to quickly ascertain if a number is larger, much larger, smaller, or much smaller than another. Additionally, imagine the time you need to spend writing all those zeros and not make an error. Engineering notation and prefixes solve this problem by bracketing numbers into easily conceptualized levels of magnitude where one number can be quickly compared to another. For those of you versed in scientific notation, engineering notation is a related technique, but it's 10 to the third times better. This technique is equivalent to learning a new language, and learning to speak a new language takes copious amounts of practice. I'm encouraging you to get involved with this lecture by pausing the lecture often and working out some of the illustrated example problems by yourself. Ideally, your answer should match that of the illustrated example problem. If not, the illustrated example problem is there to guide you to the correct solution. Engineering notation and prefixes will be used for the remainder of this playlist and others. A solid understanding of their importance, magnitude, and use is essential for any success in technical career fields dominated by numbers like electronics. The key to engineering notation is breaking unusually large and small numbers into groups of 3. This is a pretty natural inclination for those people that use commas to separate large numbers. If you use 3 digits to the left of the decimal place, you can represent a coefficient span from greater than 1 to less than 1,000, including non-whole numbers like 123.4 or 50.75. If you go 1,000 or larger, or less than 1, you're doing it wrong. Breaking these numbers into groups of 3, we can pinpoint the important part of the numbers of interest. Only the parts at the extreme left of large numbers and the extreme right of small numbers are actually important in delivering information. All the zeros to the right or left of the important part just tell us how big or small the number is. 560,000 is actually 560 times 1,000. 560 is a coefficient less than 1,000 and greater than 1. We're multiplying this coefficient times the power of 10. 10 million is actually 10 times 1 million. The coefficient 10 is less than 1,000 and greater than 1. Again, we're multiplying the coefficient times the power of 10. In this case, a million. 0.000020 is actually 20 times 0.000001, or 1 millionth. The coefficient 20 is less than 1,000 and greater than 1. Again, we're multiplying the coefficient times the power of 10. In this case, a millionth. Finally, 0.00000000033 is actually 33 times 0.0000000000001, or 1 trillionth. The coefficient 33 is less than 1,000 and greater than 1. Again, we're multiplying the coefficient times the power of 10, in this case a trillionth. This is the key to engineering notation. Take a coefficient less than 1,000 and greater than 1, and multiply it by some easily packaged up magnitude, like a trillion, a billion, a million, 1,000, 1, 1,000th, a millionth, a billionth, a trillionth, and so on. These easily packaged magnitudes only come in increments of 10 raised to some power divisible by 3. A power of 10 raised to a number divisible by 3 is 1,000, a million, a billion, and so on. This is most likely where you've been placing commas your entire life when you've written unusually large numbers. 1,000 is 10 raised to the power of 3. Or if you want to think of it in a different fashion, 1,000 is 1 followed by 3 zeros. A million is 10 raised to the power of 6. Or if you want to think of it in a different fashion, a 1 followed by 6 zeros. A billion is 10 raised to the power of 9. Or if you'd like to think of it in a different fashion, a 1 followed by 9 zeros. A trillion is 10 raised to the power of 12. Or if you wish to think of it in a different fashion, a 1 followed by 12 zeros. At the base level, i.e. at a point with no magnitude modification necessary for numbers already below 1,000 and greater than 1, these numbers can also be multiplied by a power of 10, albeit a tricky power, that of 10 raised to the 0 power. Anything raised to the 0 power is 1. On the other side of the decimal point, we use negative exponents in multiples of 3. Recall from the DC math lecture, available at the Big Bad Tech channel, a negative exponent means the base is to be shifted to the other side of the fraction line and then raised to that power. 10 to the negative third is 1 over 10, where 10 is raised to the third power. 10 to the third, as we previously learned, is 1,000, so 10 to the negative third is 1/1000th, or 0.001. If you want to think of this in a different manner, 10 to the negative third means we shift the decimal point 3 places. Similarly, 10 to the negative sixth is 1 over 10, where 10 is raised to the sixth power. 10 to the sixth power, as we previously learned, is 1 million. So 10 to the negative sixth is 1/millionth, or 0.000001. If you want to think of this in a different manner, 10 to the negative sixth means we shift the decimal point 6 places. Similarly, 10 to the negative ninth is 1 over 10, where 10 is raised to the ninth power. 10 to the ninth, as we previously learned, is 1 billion. So 10 to the negative ninth is 1 over a billion, or a billionth, or 0.000000001. If you want to think of this in a different manner, 10 to the negative ninth means we shift the decimal point 9 places. Finally, 10 to the negative 12th is 1 over 10, where 10 is raised to the 12th power. 10 to the 12th power is 1 trillion. So 10 to the negative 12th is a trillionth, or 0.00000000001. If you want to think of this in a different manner, 10 to the negative 12th means we shift the decimal point 12 places. Here's what's neat about engineering notation. Chances are you will never have occasion to use anything above or below the ranges I've presented. A trillion to a trillionth. 10 to the 12th and 10 to the negative 12th covers the spectrum of unimaginably large to the inconceivably small. 12963, base unit at 0, mirror image, -3, -6, -9, -12. Committing this simple relationship to memory should take less than 1 second of your time. Take the time necessary to commit this to memory, because someday someone's going to take it away. Just kidding. I bet you freaked out there. I'll keep this cheat sheet on the screen for now, and we'll make use of it for the first set of illustrated example problems. Be warned though, I'm going to push you out of the nest soon, and it's your choice to fly or die. Here's a collection of unwieldy numbers. I'm asking you to figure out what coefficient and to what power of 10 these coefficients are raised to. By all means, pause the lecture and take a shot at this. You might want to watch me perform the first exercise to make sure you understand what I'm asking. Our first number, 33,000, could be divided up into groups of 3 in the following fashion. Notice this is where I would ordinarily place commas if I was to write 33,000 out on paper. The coefficient in this case is 33. It's a number less than 1,000 and greater than 1. I'm multiplying this by 1,000. 1,000 is 10 to the third power. Therefore, using engineering notation, 33,000 is better written as 33 times 10 to the third. Alright, you're on your own now. Pause the lecture and see if you can do this for the remaining unwieldy numbers. Determine the coefficient less than 1,000 and greater than 1 that you would multiply by 10 raised to a power divisible by 3. For our second number, 23,800,000, I would divide it up into groups of 3 in the following fashion. The coefficient in this case is 23.8, since 3 and 8 straddle a dividing line. 23.8 is a number less than 1,000 and greater than 1. I'm multiplying this by 1 million, where 1 million is 10 to the 6th. Therefore, using engineering notation, 23,800,000 is better expressed as 23.8 times 10 to the 6th power. For our third number, 24, no modification is really necessary to make it readable. The coefficient in this case is 24. It's already a number less than 1,000 and greater than 1. I can multiply 24 times 1, or 10 raised to the 0 power, to make this apparent. For our next number, 0.196, we're on the other side of the decimal point, meaning we're in negative exponent territory. I would divide it up into groups of 3 in the following fashion. The coefficient in this case is 196. It's a number less than 1,000 and greater than 1. I'm multiplying 196 by 0.001, or 10 to the negative third. Therefore, using engineering notation, 0.196 is better written as 196 times 10 to the negative third. For our next number, 8,700,000,000, I would divide it up into groups of 3 in the following fashion. The coefficient in this case is 8.7. It's a number less than 1,000 and greater than 1. I'm multiplying 8.7 by 1 billion, where 1 billion is 10 to the 9th power. Therefore, using engineering notation, 8,700,000,000 is better expressed as 8.7 times 10 to the 9th. For our next number, 0.047, we're again on the other side of the decimal point in negative exponent territory. I would divide it up into groups of 3 in the following fashion. The coefficient in this case is 47. It's a number less than 1,000 and greater than 1. I'm multiplying this by 0.001, where 0.001 is 10 to the negative third power. Therefore, 0.047 is better expressed using engineering notation as 47 times 10 to the negative third. For our next number, 0.000047, we're again on the other side of the decimal point in negative exponent territory. I would divide it up into groups of 3 in the following fashion. The coefficient in this case is again 47. 47 is a number less than 1,000 and greater than 1. This time, however, I'm multiplying this by 0.000001, where 0.000001 is 10 to the negative 6th. Therefore, 0.000047 is better expressed using engineering notation as 47 times 10 to the negative 6th. For our next number, 2,840,000,000,000, I would divide it up into groups of 3 in the following fashion. The coefficient in this case is 2.84. It's a number less than 1,000 and greater than 1. I'm multiplying this by 1 trillion, where 1 trillion can be written as 10 to the 12th power. Therefore, 2,840,000,000,000 is better expressed using engineering notation as 2.84 times 10 to the 12th. For our final number, 0.00000000022, we're way deep in negative exponent territory. I would divide this up into groups of 3 in the following fashion. The coefficient in this case is 22. It's a number less than 1,000 and greater than 1. I'm multiplying this by a trillionth, where a trillionth can be expressed as 10 to the negative 12th. Therefore, using engineering notation, 0.00000000022 can be better expressed as 22 times 10 to the negative 12th. All of our originally unwieldy numbers have now been packaged up in engineering notation. Consider the 2 obvious advantages of this format. 1, the numbers expressed in engineering notation are far more compact and easier to write and read. There's no tangled string of confusing zeros, and the coefficient being part of the original number that delivered information is readily apparent. 2, and this is important, magnitude is easily discernible. All these numbers represented the same unit. Let's say zoinks, a fictitious measurement of surprise symbolized by a capital Z. One can easily and quickly determine that entry 8 is the largest measurement of surprise, 2.84 trillion zoinks. Entry 9 is by far the smallest measurement, at 22 trillionths of a zoink. For a quick discernment of magnitude, you can ignore the coefficient and look at the power of 10 to which the coefficient is raised. Compare entry 6 versus entry 7. The coefficient in both cases is 47. However, 10 to the negative third is 1,000th, meaning it is 1,000 times larger than 10 to the negative sixth, or a millionth. Entry 6 is much larger than entry 7. If measurements have the same power of 10, as in the case of entry 4 and entry 6, one can then look to the coefficient to determine relative magnitude. 196 thousandths of a zoink is larger than 47 thousandths of a zoink. Entry 4 is greater than entry 6, but they're both on the same playing field. Proceeding from largest to smallest, where entry 8 is the largest, at 10 to the 12th, engineering notation quickly lets us know that the next largest entry is entry 5, at 10 to the 9th, or a billion. The next largest entry is entry 2 at a million. The next largest entry is entry 1 at 1,000. The next largest entry is 3 at the base. Entry 4 and 6 are on the same playing field, however 4 is larger than 6. Entry 7 is 1,000 times less than entry 6. Finally, the smallest entry is entry 9 at 10 to the negative 12th, or 1 trillionth. Arranged in the proper order of magnitude, the entries would be as follows using engineering notation. Again, engineering notation is compact, easy to write and read, and gives a rapid means of relating relative magnitude of a given quantity. 10 to the 12th is substantially larger than 10 to the 9th, and substantially larger than 10 to the 6th. But wait, that's not all. In addition to engineering notation, we can also employ engineering prefixes. The disadvantage of engineering notation, as we've discussed it up to this point, is the not-so-pretty powers of 10 involved. Yes, unwieldy numbers displayed using engineering notation are sufficiently more compact and readable than their untamed and wild state, but they all necessitate the use of 10 raised to a certain power. Engineering prefixes replace the powers of 10 with shorthand equivalents. The base unit, being that which is multiplied by 1, has no prefix. 24 zoinks would be written as 24z. The next level up, 10 to the third, is replaced with a kilo, written as a lowercase k. 33 times 10 to the third zoinks would be written as 33kz. The next level up, 10 to the sixth, is replaced with a mega, written as a capital M. 23.8 times 10 to the sixth would be written as 23.8 megazoinks. The next level up, 10 to the ninth, is replaced with a giga, written as a capital G. 8.7 times 10 to the ninth will be written as 8.7 gigazoinks. Finally, the top level, 10 to the 12th, is replaced with a tera, written as capital T. 2.84 times 10 to the 12th will be written as 2.84 terazoinks. On the other side of the decimal point, the engineering prefixes used to replace the powers of 10 are as such. 10 to the negative third is replaced with a milli, written as a lowercase m. 196 times 10 to the negative third would be written as 196 millizoinks. 47 times 10 to the negative third would be written as 47 millizoinks. The next level down, 10 to the negative sixth, is replaced with a micro, written as kind of this U-shaped thing with a long tail. 47 times 10 to the negative sixth would be written as 47 microzoinks. If you run across units employing the microengineering prefix, you'll sometimes see people drop the tail in a text editor or software program and just write it as U. So you might see 47 microzoinks written as 47 U-zoinks. I typically pin the tail in the micro monkey, and I'm recommending you do so also until told otherwise. Continuing on, the next level down, 10 to the negative ninth, is replaced with a nano, written as a lowercase n. Our example entries didn't include any measurements at this scale, but if you did have one, like 47 times 10 to the negative ninth zoinks, it'd be written as 47 nanozoinks. Again, 47 millizoinks is much bigger than 47 microzoinks. And 47 millizoinks is much, much bigger than 47 nanozoinks because of the quick indication of relative magnitude allowed by numbers employing engineering prefixes. Finally, at the bottom end of our scale, 10 to the negative 12th is replaced with a pico prefix, written as a lowercase p. 22 times 10 to the negative 12th could be written as 22 picozoinks. Again, at the base level, 10 to the 0 or 1 does not require a prefix. The next level up, 10 to the third is replaced with a kilo, symbolized with a lowercase k. The next level up, 10 to the 6 is replaced with a mega, symbolized with a capital M. The next level up, 10 to the 9th, is replaced with a giga, symbolized with a capital G. The next level up, 10 to the 12th, is replaced with a tera, symbolized with a capital T. On the other side of the decimal point, 10 to the negative third is replaced with a milli, symbolized with a lowercase m. Note the difference between 10 to the negative third and 10 to the 6th. 10 to the 6th is a capital M. It's mega. It means it's big. 10 to the negative third is a milli. It's a tiny m. It means it's small. Don't confuse the two. The next level down, 10 to the negative 6, is replaced with a micro, symbolized by a U with a tail. The next level down, 10 to the negative 9th, is replaced with a nano, symbolized by a lowercase n. Finally, the bottom range of our scale, but by no means the bottom of the complete engineering prefix scale, 10 to the negative 12th, is replaced with a pico, symbolized with a lowercase p. 2 points. 1. Remember the significance of these prefixes. They're shorthand notation, and I'm going to expect you to know at a casual glance that a megazoink is much, much, much bigger than a millizoink, and then a picozoink is much, much smaller than a microzoink. 2. Use the engineering prefixes and the engineering prefixes only. That's the point of using shorthand notation. It replaces the ugly powers of 10 we previously used. For example, 23,800,000 zoinks can be expressed as either 23.8 times 10 to the 6th zoinks or 23.8 megazoinks. With the option employing prefixes, 23.8 megazoinks is preferred by the engineering technician community. Do not combine forms. 23.8 times 10 to the 6th megazoinks, a combination of engineering notation using powers of 10 and engineering notation using prefixes, does not mean what you think it does. 23.8 times 10 to the 6 megazoinks means 23,800,000 megazoinks. And if a mega is equivalent to 10 to the 6th, this means 23,800,000 times 10 to the 6th, or 23,800,000,000,000 zoinks, which would more appropriately be written as 23.8 terazoinks. Sorry if this diversion made your head explode. We'll return to converting between numbers employing engineering prefixes in the unit conversion lecture in the near future. For now, I want you to be able to take a wild and unruly number and just place it in proper engineering notation using engineering prefixes only. Remember, the coefficient must be a number less than 1,000 and greater than 1. The coefficient is then multiplied by 10 raised to a power divisible by 3, as in 0, 3, 6, 9, 12, or on the other side of the decimal point, -3, -6, -9, or -12. These powers of 10 are written in shorthand as kilo, little k, mega, big M, giga, big G, tera, big T, and on the other side of the decimal point, milli, little m, micro, U with a tail, nano, little n, and pico, little p. Remember this, because one day someone is going to take it away. Got you again. I'll leave the cheat sheet up for our first round of illustrated example problems, but I am taking it away once you get walking in a straight line. Start incorporating this system into your worldview. Pause the lecture and see if you can break these unwieldy beasts into tame and easily readable equivalents employing engineering notation and making use of engineering prefixes. 100,000 volts, 0.00000000002 seconds, 6,750,000 watts, 0.000000050 meters. Don't necessarily worry about the significance of the units attached to these numbers right now. Later lectures on specific topics will fill in the missing details. Our first example is 100 followed by 3 zeros, meaning this is 100 times 1,000, or 10 to the third. 10 to the third could be replaced by the kilo, or little k prefix. Therefore, this number is better represented as 100 kilovolts. The second example has a coefficient of 2, 12 places to the right of the decimal point, meaning this is 2 times 0.0000000000001, or 10 to the negative 12th. 10 to the negative 12th could be replaced by the pico, or little p prefix. Therefore, this number is better represented as 2 picoseconds. The third example is 6.75 times a million, where a million could be represented as 10 to the 6th, and 10 to the 6th could be replaced by the mega, or capital M prefix. Therefore, this number is better represented as 6.75 megawatts. The fourth example has a coefficient of 50, 9 places to the right of the decimal point, meaning this is 50 times 0.00000000001, or 10 to the negative 9th. 10 to the negative 9th can be replaced by the nano, or little n prefix. Therefore, this number is better expressed as 50 nanometers. All right, second set, you're on your own now. Pause the lecture and see if you can put these numbers into their engineering notation equivalents and make use of engineering prefixes. Some of these might seem tricky for those new to this topic. Don't tap out too soon. Struggle with it a little bit. Our first example, 69,000 volts, can be represented by 69 followed by 3 zeros, meaning this is 69 times 1,000, or 10 to the third. 10 to the third could be replaced by the kilo, or k prefix. Therefore, this number is better represented as 69 kV. The second example is a little tricky. If you break this number into a package of 3 digits, it has a coefficient of 50, 3 places to the right of the decimal point, meaning this is 50 times 0.001, or 10 to the negative third. 10 to the negative third could be replaced by the milli, or little m prefix. Therefore, this number is better represented as 50 milliseconds. The third example needs no engineering prefix, since 120 volts is an easily conceptualized number, already being less than 1,000 and greater than 1. The engineering notation equivalent of 120 volts using engineering prefixes is 120 volts. Don't mess with perfection. The fourth example has a coefficient of 17.3, 3 places to the right of the decimal point, meaning this is 17.3 times 0.001, or 10 to the negative third. 10 to the negative third can be replaced by the milli, or little m prefix. Therefore, this number is better represented as 17.3 milliamps, where an amp is a measurement of electrical current, the passage of a certain quantity of charges past a point in a given time period. The final example is 8.2 times 1 million, or 10 to the 6th. 10 to the 6th could be replaced by the mega, or capital M prefix. Therefore, this number is better represented as 8.2 mega ohms, where an ohm is a measurement of opposition to current flow. All right, third set, same song in reverse. Here are some numbers using engineering notation and prefixes. Pause the lecture and see if you can 1. Order these observations from largest to smallest, and 2. Break them open into their natural equivalents without prefixes or powers of 10. The largest prefix I see is the 5th entry, using the giga prefix. This guy goes at the top of the heap. The next largest is the 3rd entry, using the mega prefix. There aren't any entries using the kilo prefix, meaning the next largest is the 4th entry with no prefix. We've got 2 entries using the milli prefix. However, the 2nd entry at 506 millizoinks is larger than the last entry at 5 millizoinks. The next one is 506 millizoinks, followed by 5 millizoinks. There are no entries employing the successively smaller prefixes, micro or nano. Finally, the tiniest entry is the first one, employing the pico prefix. Notice, although 840 is a larger coefficient than any of the other coefficients, the pico modifier clearly and quickly indicates that it is on a level of magnitude far, far, far below than that of any of the other entries. Now we can break these properly ordered entries into their natural equivalent. All we have to do is replace each prefix with the appropriate power of 10. A giga is 10 to the 9th. A mega is 10 to the 6th. The entry using no prefix is multiplied by 1. The milli entries are multiplied by 10 to the negative 3rd, and the pico entry is multiplied by 10 to the negative 12th. Substituting in the decimal equivalents of the powers of 10 and multiplying by the coefficient, we're left with the following values, not employing engineering notation or engineering prefixes. Notice how much more unwieldy these numbers are to use and conceptualize in comparison to their engineering notation equivalents. You should be able to place any number into engineering notation and employ the appropriate prefix. Additionally, you should be able to place a collection of entries employing engineering notation and prefixes in order of relative magnitude, and then use your understanding of prefixes to break a number out of engineering notation. Remember, a number properly packaged up in engineering notation employing engineering prefixes uses a coefficient less than 1,000 and greater than 1. The coefficient is then multiplied by 10 raised to a power divisible by 3, as in 0, 3, 6, 9, 12, or on the other side of the decimal point, negative 3, negative 6, negative 9, or negative 12. These powers of 10 are written in shorthand as kilo, little k, mega, big M, giga, big G, tera, big T, and on the other side of the decimal point, milli, little m, micro, U with a tail, nano, little n, and pico, little p. Employ engineering prefixes in preference to powers of 10. Do not mix the forms. Now let's apply our knowledge of engineering notation and prefixes to scientific calculators employing engineering exponential format. Recall during the DC Math lecture, available at the Big Bad Tech channel, I not only performed a review of the order of operations, negative and fractional exponents, algebraic manipulation and rounding, I also performed an orientation to the scientific calculator, in this case the Texas Instruments TI-89 Titanium Edition. During this lecture, we used the mode key to set up the TI-89 in a fashion usable for our purposes. If you haven't watched this lecture or set up your calculator in this fashion, I'm encouraging you to do so now. For those versed in changing the mode of the TI-89, here are the important mode entries. Display digits float, exponential format engineering, exact approximate. Today's tasks are to 1. Learn to read a number displayed in engineering format on the TI-89, and 2. Learn to enter a number using engineering notation or prefixes into the TI-89. If you have a different calculator, obviously the keystrokes and display will be different, and you're going to have to figure it out by yourself. In exponential format engineering, the TI-89 always places a tiny capital E next to the coefficient and a power of 10 to the right of the E. This is the calculator's way of saying take the coefficient and multiply it by 10 raised to this power. If the calculator was displaying 2E3, it means take 2, multiply it by 10 raised to the third power, or 2 times 1,000, or 2,000. If this number represented a quantity of power in units of watts, this would be 2,000 watts, or using engineering prefixes, 2 kilowatts. You could think of the number to the right of the little capital E as the engineering prefix. Anytime you see a 3 there, it means kilo. Every time you see a 0 there, it means you're at the base unit. Anytime you see a -6 there, it means micro, and so on. Key to understanding how numbers are displayed on the TI-89 using engineering format are these 3 totally wrong interpretations of engineering format. First, 2e3 does not mean 2 raised to the third power. 2 to the third is 8. 2e3 means 2 times 10 to the third, 2,000, or 2 kilowatts. Second, 2e3 does not mean 2 times e. Notice the lowercase e, raised to the third power. Lowercase e is an important mathematical constant serving as the basis of the natural logarithm. Numbers like e and its irrational BFF pi are transcendental and play important and recurring roles in mathematics. As cool and mind-blowing as this is not what engineering format means. Engineering format 2e3 means 2 times 10 to the third. Finally, 2e3 means absolutely nothing to the outside world. Only in TI-89 calculator land does this mean anything. If 2e3 represented a quantity of power in units of watts, and you were to enter 2e3 on an exam or mention this to a coworker, you'd get the answer to that question wrong, or your coworker would look at you really strange. 2e3 means absolutely nothing. It's just a method your calculator uses to display numbers in engineering format. 2e3 means take the coefficient 2 and multiply it by 10 raised to the third power. You can think of the power to the right of e as equivalent to the engineering prefixes. A 3 means a k, a 6 means a mega, a 0 means you're at the base unit, a -3 means a milli, a -6 means a micro, and so on. Consider this batch of numbers as displayed on the TI-89 using engineering exponential format with their associated units. Pause the lecture and see if you can determine the number this represents, and then employ engineering prefixes to the unit. Don't worry if you don't know what the unit represents right now. We'll learn about these in later lectures. You might want to watch what I'm doing for the first illustrated example problem so you understand what I'm asking you to do. 47e-6 means take 47 and multiply it by 10 raised to the -6th. 10 raised to the -6 is a 1 6 places to the right of the decimal place. 47 times 0.000001 is 0.000047 farads. If we wanted to use engineering prefixes to represent this in a compact format, I could also say that 47e-6 means 47 microfarads. 3.9e3 means take 3.9 and multiply it by 10 raised to the 3. 10 raised to the 3 is 1,000. 3.9 times 1,000 is 3,900 ohms. If we wanted to use engineering prefixes to represent this quantity, I could say 3.9e3 is 3.9 kiloohms. The quantity 70e-3 means take 70 and multiply it by 10 to the -3rd, where 10 to the -3rd is a 1 3 places to the right of the decimal point. 70 times 0.001 is 0.070 amps. Using engineering prefixes, 70e-3 means 70 milliamps. Our next entry, 680e0, means take 680 and multiply it by 10 to the 0, where 10 to the 0 is 1. This represents a quantity of 680 ohms. It is unnecessary to include a prefix for 680 ohms, since this coefficient is already less than 1,000 and greater than 1. This quantity would most naturally be written as 680 ohms. 22e-9 means take 22 times 10 to the -9th, where 10 to the -9th is a 1 9 places to the right of the decimal point, or 0.000000022 farads. 22e-9, using engineering format, means 22 nanofarads. You'd think a capacitor with a capacitance of 22 nanofarads would be labeled 22 nanofarads, but it isn't. Capacitors are typically labeled in units of either micro or picofarads, and not nanofarads. We'll learn to convert between units employing engineering notation during the unit conversion lecture in the very near future. 2.3e6 means take 2.3 and multiply it by 10 raised to the 6th. 10 raised to the 6th is a million. 2.3 times a million is 2,300,000 watts. Using engineering prefixes, we could say that the power of 6 can be better represented using the mega prefix, where this is 2.3 megawatts. Finally, 1.15 E9 means take 1.15 times 10 raised to the ninth. 10 raised to the ninth is a billion, or 1 followed by 9 zeros. 1.15 times 1 billion is 1,150,000,000 watt-hours. Using engineering prefixes, I could say the 9 to the right of the E is better represented using the giga prefix. Therefore, this is 1.15 gigawatt-hours. As a preview of upcoming lecture topics, consider a hypothetical relationship between the last two entries. If a 2.3 megawatt turbine ran at full power for 500 hours, it would generate 1.15 gigawatt hours of energy. Energy, as we'll soon learn, is power times time. The units used for energy should be a dead giveaway. It's a unit of power, the watt, times a unit of time, the hour. If I had a larger turbine running for a longer time period, I would generate more energy. We'll return to this topic in the Energy and Power lecture. You should by now be well versed in reading numbers as displayed by a scientific calculator using engineering exponential format. Now let's stand this concept on its head, and rather than reading numbers, enter numbers into the calculator using engineering format. You'll be happy to know that this task is just as easy as finding a sketchy rundown neighborhood in Detroit. You can't not enter a number in engineering format. That's the point of having an engineering format. It takes the confusing pile of numbers you enter, chops it up, and displays it in an easily readable manner. As long as you're entering the right number, you can enter this number in any fashion you see fit, and the calculator will recognize to what power of 10 it needs to multiply the coefficient by to make it the most readable. This being said, entering long strings of zero is a serious pain, so I'll show you a shortcut using the exponentiation or EE key. Take for example the number 68 kiloohms. This is 68 times 10 to the third, or 68 times 1,000, or 68,000 ohms. I can enter 68,000 into my calculator by pressing 6, 8, 3 zeros, and following it up with an enter key. The calculator returns 68E3, meaning it has gone to the trouble of converting it to engineering format using its own peculiar display method. Alternatively, one can use the exponentiation or EE key. If I enter 6, 8, EE3, the calculator recognizes that I want to multiply 68 times 10 to the third power. Just write the expression as you would ordinarily read it. How easy is that? But wait, there's more. Even if you enter the number in an alternative fashion, let's say scientific notation, the calculator can do the conversion to engineering format for you. 68,000 in scientific notation is 6.8 times 10 raised to the fourth. If I enter 6.8 EE4, the calculator spits back 68E3. As long as your calculator is set up in exponential format engineering using the mode key, you never have to worry about this again. The calculator puts any number you enter it into engineering format. Consider the following three numbers. Pause the lecture and punch these numbers into your calculator using whatever method you wish and press enter. If you're in exponential format engineering mode, you should get the following results. 8.3 megawatts could be represented as 8.3 times 10 to the sixth, or 10 to the sixth is a million. Therefore, this is 8,300,000. If you wanted to, you could enter 8, 3, and 5 zeros and then press enter. The calculator would return 8.3 E6. Although effective, this seems very inefficient. Go straight into engineering format. 8.3 megawatts is 8.3 times 10 raised to the sixth. Enter this as 8.3 EE6. Again, the calculator returns 8.3 E6. Same results with less keystrokes and less math. That's the point of engineering notation. It makes unusually large and unusually small numbers less cumbersome and easier to manipulate. 39 microfarads can be represented as 39 times 10 to the negative 6th, where 10 to the negative 6 is 0.000001. I could enter this number as 0.000039. The calculator would return 39e negative 6. Again, this first method seems startlingly inefficient. Go straight into engineering format. Enter this as 3, 9, EE, negation sign, totally different than subtraction, 6. Again, the calculator returns 39e negative 6. The same results, only faster. 2.56 times 10 to the negative 7th grams is a number expressed in scientific notation. For those versed in scientific notation, you'll realize this is 0.000000256. You can go to the trouble of learning scientific notation and enter this number using the old-fashioned way. However, we're not training to be scientists. We're training to be engineering technicians. Not only do we get paid better than scientists, we're way more fun than those stuffy nerds, and we use engineering notation to get the job done. Calculator, what is 2.56 EE negative 7? The calculator returns the value of 256 E negative 9, or using engineering prefixes, 256 nanograms. Thank you, calculator. Your work here is done. That's it. This concludes the Introduction to Engineering Notation and Prefixes lecture. Keep in mind, we'll be applying the skills we learned today in all future lectures. This is one of the base skills upon which we'll build our understanding of electronics. Electronics is taught with the language of numbers, and you must have a basic fluency in this language to apply theory and interpret observations. If you're less than confident with your ability to employ engineering notation and prefixes, I'm asking you get confident in these skills before moving on to the next topic. By all means, rewind and revisit this lecture as many times as you need. Practice, practice, practice. Engineering notation and prefixes may seem like a wholly new and foreign language, but trust me, just like learning a new language, it'll get easier and more natural with repeated exposure. In conclusion, this lecture presented engineering notation, engineering prefixes, and engineering format as utilized by a scientific calculator. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource and be sure to check out the Big Bad Tech channel for additional resources and updates.